So welcome to everybody. We will be covering modeling thermal contact with contactors, and this will be within Thermal Desktop. Now, the first question would be, what is thermal contact? Thermal contact is where we have an interface between parts that transfer heat. So in this box to the right, we have cylinders, bricks, and even heat pipes that need to connect to the box itself. And it's not going to be easy to hook up piece by piece. Now, with a thermal contact, we assume that there is going to be a finite temperature difference with heat transfer. If there's zero heat transfer, the two objects are isolated. If there's zero temperature difference, if you're expecting zero temperature difference, then really you need to be modeling perfect contact. And I'll be discussing that towards the end of the presentation. But here we're talking about imperfect contact with heat transfer. And hooking things up manually, as in days of old, where you had to hook up node to node, can be very problematic. First of all, there's many node-to-node connections. Then you have to figure out any partial connections, where part of a node might be hooked up to the part of another node. And then also changing configurations. So this simple diagram I have, this first situation is not a big issue. I just hook up these two nodes together. But then as we start changing our nodal subdivision, now I have to figure out which nodes this part gets connected to. Some might go to here, some might go to here, and some might even go over to here. And let me switch over to Spotlight here. So then as we get even more complex, even for this very simple example, it becomes harder to determine by hand which nodes you get connected to. So we might have a little connection here, and if we just go straight across, then we're moving our heat over to the right, where we might actually need to spread it out a little bit side to side. So that's where we come into contactors. Now, contactors are used to create thermal contact between thermal desktop objects. These objects could be any of the thermal desktop primitive shapes, thin shell finite elements, or FlowCAD pipes. The contactors are going to connect closest nodes across the interface and also account for partial connections and even automatically recalculate if the parts move or change. What I've shown here, this is a way of checking the contactors. These are called the contactor markers. But when we display this, we see that there's going to be some connection here to here. We'd have to verify where the center point of that, where the edge of that node is, but I have a feeling that this gets connected over here. But you'll also see that this node connects to both of these nodes down here. So we'll talk about how these are calculated and work through some examples as we go through this. Creating a contactor, it's fairly simple. First thing you have to do is make sure that the objects you're connecting are already created, because you have to select them once you issue the command. So you select the thermal FDFEM network and then contactor. Select the objects you're connecting from, and then select the objects you're connecting to. Once you've done that, the contactor form will open as it's shown on the right. And then you can come in and enter in, as a minimum, the conduction coefficient, which is right here. But then you have all these other options that we'll talk about through this presentation of how you're going to do this. When you're done, best thing to do is immediately choose Show Calcs, which then shows you those test points or the contactor markers so that you can see how that connection is being made and if it's doing what you expected it to do. So let me just do a quick example. So here I already have one created. I'll go ahead and delete that, and we'll create one from scratch. So I have a small part that I'm mounting to a larger part. This might be a component on a circuit board, or it could be a box on the side wall of a container or electronics box. So I'll go to Thermal, FD, FEM Network, Contactor. Choose that. I'm going to what I'm connecting from, and I'll talk about tips and tricks later, but typically, I'll go ahead and say it now, I usually go from small objects to large objects. So I have to hit return to finish selection, and then I select what I'm connecting to, and then give it a conduction coefficient as a minimum, and then I'll show calculations. That's really all that's needed. To clear this, I can come up here to, there's a couple of options, this icon right here, the green Reset PD to Model Space. If I select that, that clears out my contactor markers. If you need to, under Model Checks, clear contactor markers right here. If you do use the menu, make sure that you choose under Model Checks, show contactor markers, not contact markers. This is obsolete, or deprecated. So show contactor markers, shows the markers for contactors that we're talking about now. The different options that we have, first option is contacting from face or edge. So for a face contact, you can connect from a thermal desktop solid, a FlowCAD pipe, or any of the thin shells, whether they're thermal desktop or finite element. When you do the face contact, the from surfaces that are active in the contactor are marked with green arrows pointing outward from the active face. For edge contact, you can use thin shells, either thermal desktop or finite element, or FlowCAD pipe center lines, which is a very convenient method to hook up FlowCAD pipes. There, the from arrows are going to be shown along the edge that's active. So you'll notice that just two edges here are active. Any object that we're connecting to will have arrows pointing inward towards all the faces of that object. So you don't actually choose which sides are active for the two objects. It's just going to find the closest. So let me switch back over to this example, and you see the arrow coming up from here. Now this shows that the top face is active, and I'll talk about it in a minute, but this point algorithm can be up or down. It's omnidirectional, so it doesn't matter. If I were using the ray trace algorithm, then I would definitely have to point in the right direction. But to change this, I can select this, select Edit From Objects, and then either I could check just bottom, or I could check both if I need contact from both of those faces. And that would double the area that I have as a per area. The input value type is the next option. Your choices are per area or length, or absolute. Where per area or length, the conduction coefficient is multiplied by the contact area or the edge length of each node. That gives you the distribution along the surface or the edge, and that gives you your total conduction as you go through. The absolute, you provide the total conductance available And then you have choices inside of that of what to do if you're not 100% connected. If you're not 100% connected, you can choose to reduce the conductance as a fraction of what's connected, and then it gets distributed among the nodes based on contact area. Or you can say it's always going to use the total conductance is equal to the input value. And this just simply distributes among the nodes for the contact area. Now the absolute is very useful for situations like per item coefficients. So you may be provided a value that says my conduction coefficient per bolt is this value, let's say 5, and let me show an example. So if these were bolted together and my test data shows that I have a conduction coefficient of 5 per bolt, first thing I'm going to do is choose total conductance. And then probably the easiest thing to do is go ahead and double click in this field. And I would say it's 5 per bolt. And then I have 8 bolts that are holding this down. And when I say OK, that comes back with 40, which is my total, and that will be distributed over the entire connection. Now, one thing to point out is that the area is always calculated using the from objects. So that's why it's important to choose what you're connecting from and then what you're connecting to. So what you're connecting from is actually being used to calculate the area of contact. One thing to always do is test simple models until you have a full understanding of how this works. Make sure it behaves as you expect, so you can verify that, okay, yes, that was what I expected it to do. So you can use that in your more complicated model. Another option you have available is to use material. So this allows you to model a material in the interface. So I'm connecting from this top object to the bottom object, and I might have something like a gasket or a gap pad or something else in between the two parts that I don't want to explicitly model. So when you choose material or use material, you'll have the option to choose, or not option, you will choose a material from your materials database, and that will provide the conductivity through the interface. Then, depending on your input value type, determines what you have to provide. If you choose absolute, then you must provide the contact area divided by the material thickness. If you think about this, the conduction through this is conductivity times cross-sectional area divided by distance through the material. So Ka over L, K comes from the material, and then you provide the A over L for that. If it's a per area or length option, then if you're contacting from a face, then the contactor calculates the interface area. So the only thing that's left is the material thickness through the material interface. And you provide that as thickness, so you don't have to take the inverse or anything like that. When contacting from an edge, the contactor calculates the edge length of the contact. So now you have to provide the thickness of the edge divided by the thickness through the material. So if we look back here at our form, and I choose, let me clear this out. I choose use material, and I might choose my material here. Here you'll notice that the conduction coefficient is now an area over thickness. So I've got my conductivity here. If I choose per area, it calculates the area, and all I have to do is provide the thickness through the material. And then if this is an edge It even tells you thickness of contact area divided by length through the material. So this ends up being unitless. If you're unsure of how this works, try a simple test, something you can do an envelope calculation, just a hand calculation, and compare it to what is output by the software. Another option that's available is radiation. So this would be where you just have a radiation heat transfer through the interface. It will create the radiation conductors. Just to let you know, this is for just simple interfaces with a known form factor. So parallel plates, concentric cylinders, things along those lines. If it's complex radiation exchange for much more of your model this with RadCAD, because then it takes into account reflections and anything else that can't be done by a simple calculation. Then based on your input value type, if you choose absolute, you're providing the radiation conductor, or RadK as we call it. And this is the area of the from surface times the effective emissivity times the view factor from the from surface to the to surface, so I to J. If you have a per area or length, if it's contact from a face, you provide the effective emissivity times the view factor, and the contactor calculates the interface area. If it's a contact from an edge, the contactor calculates the edge length, but then you provide the effective emissivity times the view factor multiplied by the edge thickness. So if we take a look at this again, so instead of using material, I'm going to use radiation. You'll see emissivity. Now Bij is our term for the form factor. But we can do per area or length, or if we do absolute, then this is a RadK. And then edges per length. So it's the thickness. So that's the width of the interface, and then the emissivity times the Bij. The next option is available no matter which of those other options you choose, and that is if your surface has, let me select this and edit. If your surface or your solid has insulation on it, and I put insulation top and bottom, and then I might choose, so I've got this insulation material, and it has some kind of thickness to it. Now that insulation is not visible on the screen unless you do a certain model check. But when I want to create my contactor, I have to determine if that contactor is going to connect to the insulation or to the surface underneath the insulation. So with this unchecked, it goes underneath the insulation. And then if with this checked, it connects to the insulation itself. So let's take a look at that. As this diagram shows, this is the insulation that would not be visible, but this is what the connection would look like. So if that box is checked, this is sitting on top of the insulation, otherwise it's underneath. Now, just to keep in mind, this does not mask the insulation itself. So, you know, if you need something a little more descriptive, you would have to explicitly model this where you might have this buried inside the insulation. The last option last option we'll talk about on the chart are the inputs for the calculation algorithm. Now, when we're doing these contactors, we have to estimate how much contact area there is. So to do that, we subdivide the surface or edge into integration intervals. These subdivisions are used for testing the nearest node. So we can look at, this is what we call the point algorithm. Each one of these starting points is an integration interval. And so this finds the closest surface and the node associated with that surface. So even all the way out to here. With faces, the subdivisions are in two directions. If we ask for 10 integration intervals, we'll get 100 test points on a surface. The higher the number you provide, the higher your accuracy, but the slower the calculations. For most purposes, the default of 10 works very well. Tolerance is a way to limit connections based on distance. By default, we have a very large value in there, and it will connect everything on the from object. If you reduce the tolerance, it allows you to have disconnected sections based on distance. And so if you have a surface that extends beyond, now let me do this. First, don't need insulation nodes. We'll start off with this primary tolerance, and I will say, okay, let me move this surface. And then I'm going to test my contactor. So let me check it. There's an icon here, show contactor markers. And then if we look over here, let me switch to the side view. We see that everything gets connected. Now, if I come in here, I'm going to do a measurement test. So I use distance, and I'm going to measure from there to there. And that's about, where are we, delta Z, 0.2 would get it for me. So let me clear these out. So reset TD model space. I'm going to edit my contactor again. And then I choose here, I'm going to put in 0.02. Show calcs. And so this brings up a window that says I didn't fully connect, but I set it up that way. I can dismiss that. And this shows that, part of this has failed, the tolerance test, but I'm only connecting this portion over here. Now that leads right into the point algorithm versus ray trace algorithm. The point algorithm is omnidirectional. So even though I had a slightly large tolerance, or too large, I picked up this little piece out here, a little bit of that connection. But let's say I want to switch to ray trace algorithm. I'll clear those, edit, so thermal, edit, and then I switch to ray trace algorithm. This is going to shoot a ray from each of the test points and see if it hits a surface or a node on the to list. So let me show calcs. And this tells me 50% complete, which means I'm 50% connected, which is really what this should be, because that surface is evenly split, being over the lower object and not. So the ray trace algorithm is great for situations like that where you have parallel faces with a gap. So they have to have a gap because just like radiation, you can't have two surfaces in the same plane. So if you have a gap, parallel faces, the ray trace algorithm is going to do a great job with that. On to some tips and tricks. First one, and I've been doing this all through this, is check your connections. Verify that it's what you expected. There's several ways to do this. One is directly from the contactor edit form that I've already shown. I also showed this icon over here, show contactor markers. Under model checks, show contactor markers, another way. And then the last way would be in our model browser. If you list by contactors, then I have this contactor. I'm going to right click on it and I can show contactor markers. And that goes to the exact same situation. Another tip is to limit the faces and edges that participate. I'm going to open up another model that has edge contactors. And not yet, but it will. So I'm going to create a contactor. I'll select that surface, and then I'll select this surface. And down here, if I said, well, I don't know what I'm going to connect to, I'll just connect to everything. And then I come in here and say show contact or show calculations. This connects every edge up to that lower board, which is most likely not correct. I could go through and use the tolerance to limit just to the bottom edge, but then I'm doing all these tests around here. So that's inefficient use of my test points. So a much better way is to make sure that you're picking just the right faces that you want. And that leads to my next tip, or this is actually a trick, is selecting in wireframe actually allows you to pick specific edges. If I switch over to wireframe mode and I create a contactor, I can come down here to this bottom edge and you'll see that it says along X at Y equals 0, and I'm going to select that, hit return to select my two objects, select that, hit return, and now when I show calcs, all the connections are right along the bottom edge and the one that I intended. Now, what happens if my model is more like this one over here, where I'm connecting from finite elements? Now, I could come through and click on each one of these, but this could be a fairly complex model. So what I'm going to do is I'm going to create a contactor, and then to select, I'm going to use the fence mode. I could just type in F for fence, but I'm going to type it all in. And I'm going to pick a series of, I can just do lines, and I can do line segments. So this one just comes all the way through here. Hit return, and then I'm going to hit return again because now I'm still selecting from objects. Select my two object there, and then hit return. Here I need to, it has first edge, second edge, third edge, and it's all based on what I drew my line across. But that's not what I want. What I want are the free edges on that surface. Now the first thing I'm going to do is just say OK, just to show that all it did was pick the edges that I picked. But once I do that, I'm going to come back and edit, and I could have done this to start. I can right-click in this list, and I'm going to say calculate free edges for elements. And the first thing you'll notice is that some of these don't have an edge selected, which means that's why they go red. But those are the ones up here where just a point comes down to the bottom edge. So now if I say OK, now I have exactly the edges that I wanted off of those finite elements. These other two I'm not going to show, but using domain tag sets, typically domain tag sets are used to bring in lists of objects from either XREFs or an imported mesh, such as those from TD Direct. And then contactors can reference domain tag sets. And then if you make a change in either the XREF or in the mesher and re-import that mesh, now the contactors can update automatically to whatever's now included in that domain tag set. Another possibility, especially with TD Direct, is you can create matched meshes where the meshes are aligned so you have a one-for-one correspondence. And when you have that one-for-one correspondence, you don't need 100 test points to determine that you're 100% connected. You only need one. Change your integration interval to 1 and the calculations will be much faster. Now, next topic I'll go over are some common mistakes. The first common mistake, and I mentioned this earlier, is I tend to go from small objects to large objects, and the mistake is to connect from large to small. Now, the problem with this is that the surface area is calculated using the from surface. So it requires using the tolerance to prevent overestimation of the contact area. And then all those failed test points are inefficient uses of your integration intervals. Now, let me go through I'll go through an example, but how you find these situations, one, we will provide some warnings that will pop up. But mostly in the model browser, you'll see contactors that are marked as red. That means that the from area is larger than the total to area. If they're green, that means that you're going from small areas to large areas. And then I'll show you how to fix it. It's as simple as clicking a button. So let me go back to this object, and I'm going to just edit the contactor from here. And I'm going to go ahead and do this. I'm going to switch it. Actually, I take that back. I'm going to clear and delete this contactor. Coming back to my thermal ribbon, create a contactor going from the large object to the small object. Give it a value. When I show my calculations, it shows me that the entire surface area is connected. So it's using an area equal to this large surface down here. So in order to reduce that, I need to now reduce my tolerance. I'll show that one more time. To 0.02. Say OK, and then show contactor markers. There we go. A lot of test points or nodes are 0% complete, so a lot of failed test points. So it's an inefficient use of those. So again, sorry, going back to that. If I need to reverse that, I edit my contactor and then just switch the arrows. Now the one thing I will have to do is go through and make sure I've got the correct top and bottom sides. It doesn't remember that. So I have to go back and reset whatever's active. Another common mistake is using centered nodes in the direction of the heat flow. And if you're using a contactor and connecting to the edge of a surface that has centered nodes or to the face of a solid that has centered nodes, these are actually solids that are transparent. But what happens is the material between the node center and the node edge or face is not included in the conduction network for these centered nodes. So these both have 10 nodes, but if you look over here, with edge nodes, we reach the closed form solution with just 2 nodes. Very, very straightforward. With edge nodes, we have not even reached the closed form solution, and we're about a degree off all the way up to 100 nodes through this object. So whenever you have the heat flow going in the direction of the nodes, then you need to have edge nodes included. Another common mistake is using contactors to model perfect contact. Now, the problem with this is that contactors will always have a non-zero temperature difference. A large conductance can cause extremely small time steps because the time step algorithm uses the capacitance of the node divided by the sum of all the conductors. So if you make one of those conductors really large, then your time step goes very small. Another situation that can happen, and that's what the diagram is all about, is a short circuit is actually created when your nodes are offset. If you are, and I guess yesterday I said I should have switched these and I forgot to, but the best option for modeling perfect contact is to merge nodes, which requires them to be aligned. If you can't merge nodes, then you should at least try to align them as best as you can before using a high contact conductance. This fixes the short circuit, but not the time step. Then to follow that up, reduce your conductance coefficient from an extremely large value down so that you have an acceptable temperature difference in your model. Depending on your model, it could be 1/10 of a degree, it could be 5 degrees, whatever is acceptable, accept that, and that will increase the speed of your model without introducing too large of an error in there. One thing I would like to point out, this little sample shows a short circuit that a user pointed out to us. If I take this bar and increase its thickness or its width by 50%, then the temperature at the heated end is 368.7 degrees. If I take this, and at the very least, this should be a little bit warmer over here because you have less conduction at the ends. But what I've done is I've created a masonry type, so brick layer layout here where I've got nodes connected to each other. When I start from a very low conductance value, it acts as though this were just the one bar here. So there's very little additional heat transfer with this bar. And that's where you see this back up at the 402 like we talked about with the centered nodes. As I increase that conductance, I now start going below the temperature for 150% of the material of this primary bar. And what that's telling me is there's a short circuit that's happening. And what happens is when you have a large conductance, you're saying that these two nodes should be the same temperature. Well, this node should equal this node, but this node also should equal this node, and so on down the line. So you end up actually having a short circuit through this system. The best option, if you do have to model high contact conductance values in a contactor, make sure your nodes are well aligned so you don't get this short circuit problem. Okay, well that's the end of the presentation. In summary, the contactors provide a very convenient method of modeling thermal interfaces. There is automatic calculation of nearest node pairs and estimation of contact area or length, and it's automatically updated if your geometry changes. There are many options for customization, including connecting from faces or edges, putting material in the interface, using radiation in the interface. So there's a lot of possibilities here with the contactors. Looks like, as I look over here, there's only been one question, and that was when my audio dropped out. We do have some time now for questions. If anybody does have some, you can type them in the question pane.